Welcome back to Hansen theory. You now understand polymers, solvents, pigments, curing, environment effects, and modern coating systems. Today we move into a domain most engineers underestimate: specialty additives. Dispersants, surfactants, rheology modifiers, defoamers, flow agents, wetting agents, and stabilizers are often treated as small helpers. In reality, additives are molecular force modifiers. They reshape interaction balance inside your formulation. They shift Ra distance. They change red values. They decide whether your coating becomes stable, smooth, and durable, or unstable and unpredictable. Let's begin with the core concept. Additives do not work by magic. They work by altering dispersion forces, polarity, and hydrogen bonding at interfaces. They act at boundaries. Polymer solvent, polymer, pigment, 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 air, liquid, liquid, substrate. Every interface has its own interaction imbalance. Additives exist to correct these imbalances. Now, let's break this down by category. First, dispersants. Pigments have high surface energy. Resins often cannot fully wet pigment surfaces on their own. This creates large Ra distance between pigment surface and polymer phase. Red increases. Flocculation begins. Dispersants attach to pigment surfaces using polar or hydrogen bonding interactions. At the same time, their polymer-compatible tails interact with the resin matrix. This creates a molecular bridge. In Hansen space, this effectively moves the pigment point closer to the polymer point. Ra decreases. Red drops below 1. Stability improves. This is why wrong dispersant selection destroys dispersion, even when solvent and resin selection are correct. Next, wetting agents. Wetting agents operate at solid, liquid, and liquid, air interfaces. Their job is to reduce surface tension mismatch. From a Hansen perspective, they modify interaction balance at boundaries. When wetting is poor, dispersion forces dominate unevenly. Contact angles increase. Substrate adhesion suffers. By selecting wetting agents with compatible Hansen parameters, engineers align molecular forces across interfaces. This improves leveling, adhesion, and substrate coverage. Now, let's talk about rheology modifiers. These additives are not just viscosity controllers. They interact with polymer chains and solvent molecules. Some form hydrogen-bonded networks. Some rely on associative thickening through polar interactions. If Ra distance between rheology modifier and polymer is too large, performance collapses. You see phase separation, gel instability, or viscosity drift. Minority thinking engineers treat rheology additives as interaction network components, not viscosity knobs. Next, defoamers and air release additives. Foam is an interface problem. Air bubbles stabilize when molecular forces at air-liquid boundaries are balanced incorrectly. Defoamers disrupt hydrogen bonding and surface polarity at bubble interfaces. They create local incompatibility. This forces bubble collapse. In Hansen space, defoamers intentionally introduce localized interaction mismatch to break foam stability. This is controlled instability for functional benefit. Now, flow and leveling agents. Flow defects occur when surface tension gradients exist during solvent evaporation. These gradients originate from interaction imbalance. Flow agents redistribute molecular forces across the film surface. They stabilize dispersion and polarity gradients. This prevents craters, orange peel, and surface waviness. Again, this is not random chemistry. It is force engineering. Now, let's discuss additive conflicts. One of the biggest formulation mistakes is stacking additives without understanding interaction overlap. Example: a dispersant improves pigment wetting. A rheology modifier increases hydrogen bonding density. Together, they raise local polarity beyond tolerance. Red locally exceeds 1. Pigment flocculation returns. This is why additive synergy must be evaluated in Hansen space, not by supplier brochure claims. Next, additive concentration effects. Additives are powerful even at low dosage. Small changes can cause large shifts in Ra distance. Overdosing can destabilize systems. Underdosing leaves incompatibility unresolved. Minority-thinking engineers treat additive concentration as a precision adjustment tool, not trial-and-error tuning. Now, consider environmental interaction. Temperature and humidity affect additive behavior. Hydrogen bond-based additives respond strongly to moisture. Surface-active additives behave differently at high temperature. Engineers who ignore this see seasonal failures. Engineers who model additive interaction shifts maintain performance year-round. Now, let's connect additives to curing. Some additives interfere with cross-linking by blocking reactive sites. Others enhance curing by improving molecular mobility. From Hansen theory view, additives can increase or decrease effective RA distance between reactive groups. Understanding this prevents curing inhibition problems. Next, production scale behavior. Shear during mixing can change additive distribution. Spray application redistributes surface-active molecules. Drying reorganizes additive orientation. Minority-thinking engineers design additive systems that remain stable across processing steps. Now, here's the most important mindset shift. Additives are not extra ingredients. They are interaction control devices. They fine-tune molecular force balance when base formulation components cannot achieve perfect compatibility alone. This is why world-class formulations often use fewer additives, but with precise selection. Not more additives. Better interaction design. Finally, advanced engineers integrate additive selection into full Hansen modeling. Pigment-polymer compatibility adjusted using dispersants. Polymer, solvent alignment stabilized with flow agents. Interface tension corrected using wetting additives. And network mobility adjusted using rheology modifiers. Bubble instability introduced intentionally using defoamers. Everything connects back to RA distance and red behavior. This is how additives become engineering tools instead of formulation guesswork. In the next episode, we will explore real industrial case studies showing how Hansen theory solves actual coding problems in automotive and industrial applications. If you want to stop guessing additive packages and start designing interaction balance with precision, stay with this series. This is Hansen theory.